Okay, so let's come to the maths. And I don't quite remember what I actually called my talk. It was probably something quite generic. But what I wanted to call my unofficial title is what really bothers me when I think about the Tutte polynomial. So what makes me unhappy? And this comes about because there are many wonderful results for the Tutte polynomial. But a lot of these results have some sort of restriction to them. So they don't hold for all graphs or for all matroids. They hold for maybe something like plane graphs would be an example, or for regular graphs, for regular plane graphs, and so on. And this is just something that bothers me. I mean, should these results really hold in a restricted domain? So the Tutte polynomial is a graph polynomial, it's invariant of graphs. So should my result not hold for all graphs? And it makes me a bit unhappy. So it's kind of a question. So I like to think of it as sort of finding out where a result lives. So if I have some theorem and I want to follow it home and find out whether it's going to the world of graphs or matroids or plane graphs and so on. And I like to watch lots of detective movies, and I think private detectives like to put a tail on things to follow them home. So today I just want to talk a little bit about what happens when you put a tail on one of the results in the Tutte polynomial, and you just kind of follow this home and see where it leads. But before I do that, I should actually not assume that everyone knows what the Tutte polynomial is, so I'll give you just a very brief introduction to the Tutte polynomial. So what's a Tutte polynomial? Well, basically it's a polynomial valued graph invariant. So what does that mean? Well, you feed it in some graph and it spits out some polynomial in two variables x and y with coefficients in z, two non-negative integral coefficients. So for example, the Tutte polynomial of 3-cycle, you've got here of x squared plus x plus y, and of the theta graph down here, you've got y squared plus y plus x. So how do I compute these? I should at least give you some idea of some definitions of them. And I'm just going to give the two most common definitions, many, many definitions. So the first of these is the state sum. And what's happening here is that you're summing over all of the subsets of edges, and for each summand, you're just going to take a polynomial in variables x and y, and this polynomial is determined by the rank of the graph and the rank of the spanning subgraph on A. So this is going to be equal to the number of vertices in the graph minus the number of connected components of the subgraph VA, so all of the vertices of the original graph and just the edges in it. So it's a little example here. Here's my 3-cycle again, and down here we have all of the spanning subgraphs. Maybe down here, let's look at this term. So my graph is rank 2, the subgraph is rank 1, so I've got my 2 minus 1 from my x terms. And my A up here, this is the number of edges in the set, so I've got 1 edge, and the rank of this any of these subgraphs is 1, so I'm getting a y to the 0. So overall I'm going to get this 3x minus 3 term, and I go through and I do this for all of these 8 or the other 7 of these subgraphs, and add them all up, and I get the Tutte polynomial of x squared plus x plus y. So the other definition that will come up is the deletion contraction definition. And the idea here is you take your graph and you pick an edge, you delete the edge and contract the edge, and you get a pair of new graphs. And depending on whether the loop is the edge is a bridge, a loop, or ordinary, you're going to do something slightly different. And if it's a bridge, you're going to bring in an x variable and a loop, a y variable. So for example, with this theta graph down here, if I delete this bottom edge, I'm going to get this graph here. If I contract this bottom edge, I'll get these two loops. And I just keep working down this resolution tree. So delete this edge, get this, contract this edge, get this loop. And then what do I see? I've got some edge that's a bridge. So I contract it to a vertex, but I bring in a coefficient of x. This guy, contract the loop, bring in the coefficient of a term y, and I keep going on down this chain. I've got 2 loops, so I get a y and a y, and just sum up everything I've got at the bottom, and that's my top polynomial of my my theta graph. So maybe I should say that I don't expect you to memorize these definitions, the exact forms. They're not too important, but what I want you to remember is that there are these 2 definitions that we consider, and there's one of them is deletion contraction, and the other one is the state sum definition, and within that it has this rank term, so the rank of the spanning subgraph. Okay, so that's all we need to remember to go forward. So maybe I don't want to say too much about this, but it's this deletion contraction definition that gives the top polynomial its importance, and that it's kind of in a very concrete sense the most general deletion contraction graph invariant out there, which means it counts lots of wonderful things. So some of them kind of expected, like evaluating at 2, 0 gives the number of spanning forests. You get the number of proper graph colorings or nowhere 0 flows. But you can start getting more fun things like the number of tetromino tilings for locally, sort of planar lattices, and a slightly larger class of that. And fun things like evaluating at 3.5, you're getting a number of acyclic suborientations. So some of them kind of expect, and some of them really quite weird and wonderful evaluations. Crops up in a bundle of applications, so things like network reliability codes, chip firing, knot theory, statistical physics, and so on. And as you would expect from a rich object, it has lots of wonderful properties. And today I'm just going to focus on kind of what's one of the most fundamental ones, so duality. Okay, so it's not too difficult a property for the top polynomial, but it's really fundamental to the subject. Okay, so quick mention of duality, so quick reminder. So what we're doing is we've got some graph. I draw it in the plane, so we're dealing with plane graphs, and I'm just going to form a new graph from it. So in each of the faces, I'm going to just whack in a vertex. And whenever 2 faces are adjacent, whenever there's an edge defining them, I'm just going to throw an edge in, like so. And I've got a bridge here, so I'm going to add a loop. And this is my dual graph, which I've drawn over there. Okay, so something we're all very familiar with. Now, the top polynomial is really well behaved with respect to duality. And there's this wonderful duality formula that tells you if you've got a plane graph, the top polynomial of the dual graph is equal to the top polynomial of the primal if I switch the variables y and x. So up here, if I want to know the top polynomial of this red graph, I know this if I know the top polynomial of the yellow graph, I just switch the variables y and x. And as an example, we've already seen an example because the 3 cycle and the theta graph are planar duals of each other, and you can just check that t of xy is equal to 1 is equal to t of yx. So I like to pause whenever I see this result because it's really, really lovely. I think we should just stare at it for a moment. It just makes me happy. It's just a really, really nice result. Really beautiful equation. And I've stared at this for a long time in my life, and I think it's lovely, but then there's sort of a little niggle in there. It starts to make me a little bit unhappy. And there's this word plane in there. So why is the word plane in there? So we've got this lovely duality formula, but it holds for plane graphs. It doesn't, we come back to this property, so where does the result actually live? So what setting should we be considering this? It's not really a graph's result. It doesn't make sense to try and compute the top polynomial of K5 from his dual. Well, what's the dual of K5? So is it a graph invariant result, really? It's not a graphs result. And you start worrying about, well, is this actually a result about plane graphs or planar graphs? You know, it's to form the dual, I need a plane graph. So it's actually embedded in the plane. But the result still holds for planar graphs. So I start to worry about the details. And I start to think, well, there's something quite, it's a lovely result, but there's something not quite natural about this. So I've got the result for plane graphs, but there's something else going on. So this is kind of coming back to putting my tail on, my private detective tail, and finding out where this result, this very basic result about the top polynomial, lovely result about the top polynomial, actually lives. So what I'm going to do in the talk is I'm just going to work through, and we're just going to just follow this result home and just work with it and see where it takes us. Okay, so we've got this plane result. Well, how can we get rid of it? So there are a couple of options we can do that. So option one is that we could just abandon graphs altogether. And, well, what am I doing? I'm giving it a talk to matroid theorists. So you see this expression for the top polynomial, and it's got this R term, so an R of G or an R of A, and you're thinking, well, R to a graph theorist means rank of a graph, but R to a matroid theorist is just the rank of a matroid. Okay? So I can just go through and just replace my G's for my M's, and I end up with the top polynomial of a matroid, which was first defined by Crapo in 1960, 67 maybe. Maybe I'll just do a little 60 and then something unclear. And it was also in Tutte's thesis as well. Implicitly, but in the language of nets, which are representable matroids. So we've got the top polynomial of a matroid. So why is that nice? Coming back to duality, well, unlike graphs, the dual of a matroid is always defined. We can define that with no problem whatsoever, so it makes sense to talk about T of M dual. What else do we know? Well, with matroids, duality changes deletion into contraction, vice versa. So the contraction in the dual is equal to the deletion in the primal, all dualed, and similarly, delete the dual is, I can get that by contracting in the primal and then taking the dual of the result. So I can take this deletion contraction result and my fact that M is always defined, and then go to my deletion contraction relations. Remember this deletion contraction definition of a top polynomial, and just feed this in, tidy it up a little bit, and I end up with this beautiful little duality formula again, and I have it without restriction whatsoever, so I no longer have to deal with plane graphs, I'm dealing with matroids. So what does that tell me? Well, maybe above the plane graphs, I have matroids sitting there. And that's fine because, well, I can recover the plane graph because as long as I'm in the plane, the cycle matroid of the dual is equal to the dual of the cycle matroid, and I recover my classical result. So I'm happy about that until I'm not so happy about it. So what did we see? So in this proof of the duality formula, we went through the deletion contraction relation. But there's another way we could do this. We could just go through and rewrite the rank functions. So what would that involve? We want to show that if we have the exponent of the x term, this is going to get switched to the exponent of the y term under duality. Okay, so we just want to switch these terms. So how would we do that? So remember what we're trying to do is up here, so just duality switches the R exponent, the rank exponents to the nullity exponents. And down on the right here, I have this big splodge of algebra. Don't try and absorb it all, but what's going on? So I take the x exponent, I'm going to multiply by 2 just to avoid fractions. and I take my ranks, I expand it, so I'm getting a number of components. But at this point, I'm still working with plane graphs, and in many ways, components are really nasty for topological graph theory, and I don't like them. I want to deal with other things. So then I can go over and make use of Euler's formula, which is down here, to get rid of the components. I can just substitute it with the number of vertices, edges, and the number of faces of the graph, or the number of boundary components of the graph, if you prefer that language. So back here, so I kill the exponents, I bring in the faces, I tidy up a little bit. I remember, okay, so E, size of E minus size of A, that's just the size of A complement. My faces of the graph of the primal, well, duality turns faces into vertices, so that's just the number of vertices of the dual. And I can turn the number of boundary components, number of faces of the induced subgraph, sorry, the spanning subgraph on A, into those in the dual, by just noticing that the subgraph on A in G and the subgraph on A complement in the dual will have the same boundary components. So why is that? Well, we go to this picture down here, and we see if I draw a little boundary component around the blue graph, which is a spanning subgraph of the primal, well, and if I draw some same, all of the boundary components of these complementary spanning subgraph in the dual, I just see I've got exactly the same boundary components. So what have I done? I've switched into the dual, Euler's formula again, and tidy up and get my y exponent down here. So that's all great and very well and good, except for the fact. So remember, we had this plane duality formula, so what's going wrong? Well, what's going wrong is that this term that I've called Euler's formula isn't really Euler's formula, because Euler's formula has a minus gamma of G in there, where my gamma of G is called the Euler genus, and that's either twice the genus, if my surface is orientable, or is just equal to the cross-cat number if it's non-orientable. So a torus would have Euler genus 2, a real projective plane would have Euler genus 1, and a Klein bottle would have Euler genus 3, and so on. And then what's happened? Well, the plane has Euler genus 0, so we've never had to worry about what happens to the gamma in all of this calculation. But if I go back to the calculation and I find that, well, most of it just carries on fine, not worrying about this gamma, so how can I deal with that? Well, I could just bring them in at the start. So I could bring in a plus of R of G and a minus R of G, sorry, plus gamma of G and a minus gamma of G of A up here. This would carry through to the next step. Then it vanishes when I apply Euler's formula and comes back in at the end. And down here, I'm going to end up with a minus gamma G, so gamma of A complement in the dual graph. Okay, so I'm picking up an Euler genus term there. So what's happening here? Well, I can go through my plane duality results, and I can just bring in these gammas, and whenever I see a rank term in my Tutte polynomial, I can just update this by the rank plus 1/2 of this Euler genus, y 1/2, because in the last calculation I had this little factor of 2. And if I call this my sigma of G, just to give it some name so I don't have to keep writing this, and I take my definition of the Tutte polynomial where I had a rank, I replace that with sigma, I get a new graph polynomial down here. And this graph polynomial isn't completely new. This is actually a two-variable specialization of the Bolivash-Riordan polynomial. So they introduced a three-variable topological Tutte polynomial in 2001 and 2002, and this is just a two-variable specialization given by sticking z equal to 1 over root xy, which seems to be a much natural thing. Okay, so what does this tell us? Well, on the last page, we've just had a proof that with my new Tutte polynomial, or ribbon graph polynomial, as it's known, the polynomial of the dual at xy is equal to the polynomial of the primal at yx. But the important thing is that all of this holds without any restriction of planarity. So what I've done here, well, I've started off with this classic result about plane graphs and been a little bit unsatisfied with it, and I've just tailed it home to see where it takes us, sort of kind of just follow the mathematics and see where we need to go to understand the result and what's going on. And the issue is that we've ended up in matroids and embedded graphs. And yeah, that's a little unsatisfactory. So should we really be ending up with two things? It's not really nice mathematics. It indicates something missing. So there's something sitting above all this. So what's sitting above it? Well, it's kind of in one direction. What are we doing? So we're going to embedded graphs. It's got plane graphs for the classical result, or graphs and surfaces for the more general results. And matroids don't play in many ways well, very nicely with embedded graphs. And instead of matroids, you want to start considering delta-matroids. So again, I don't want to assume that people know what these are. I think knowing what a matroid is safe. So let me just give a very quick introduction to these, just give you some idea of how they could arise. And since we're working with duality a lot, so I'll just introduce these through duals. Okay, so I'm always going to be thinking of matroids in terms of their basis definition. So in this case, what's a matroid? Well, it's just a pair. I've got my ground set T, and I've got a set B, which is some collection of subsets of E, so some collection of the bases. And my dual, and I'm following the dual matroid, well, my ground set doesn't change, but my bases, how do I get my new collection of bases? Well, I just toggle every element, so I look at each basis, so each set in B, and I just toggle what is the membership of each with E. So I look at B, and if something is so I look at E, and if my element is in B, I'm going to take it out, and if it's not in B, I'm going to take it in. So back down in this little example, so what's going on? Let's complete this. So in my B, I've got the set containing 1, the set containing 2, the set containing 3, and the ground set 1, 2, 3, 4. So toggle all of the elements in E, 1 with all of the elements in E. So I'm going to get what? So 1 comes out, then 2, 3, and 4 are all going in. So 1's not in the set 2, so that goes in, and 2 comes out, and 3 and 4 are there. And with the last one, so we've got 3, so I'm toggling E and 3, so I'm going to get 1, 2, and 4. And I've got my dual. Okay. You've seen this before. So what can I do with this? Well, actually, I can localize this construction, because what am I doing? I'm looking at B and I'm toggling elements with the ground set. But instead of taking the whole of the ground set, I could do this with some subset of the ground set. So I can kind of localize the construction. I don't have to form dual globally with respect to the whole of the matroids. And this gives the concept of a partial dual, or also properly known as a twist. And what I do here is I've got some subset A of the ground set, and I'm going to take my set of bases, and I'm just going to toggle the elements that are in A, rather than the whole ground set. So what's going to happen down here, so again, I've got my B, the set containing 1, the set containing 2, the set containing 3, and I'm going to take A to be 1, 2. Then my B symmetric difference A, so what I'm doing, I've got this set 1 and B, and I toggle with 1, 2, so the 1 comes out and the 2 goes in. I've got 2, so the 1 goes in because it's not in 2, and the 2 comes out, so that becomes a 1. And for my 3, well, 1 and 2 are not in that set, so I'm going to have to end up with 1, 2, 3. There. So I end up with a new collection of sets, a new object. So my E and this new set given by toggling. And of course, this is no longer a matroid because, well, what's in my collection of bases, if you like, have different sizes. But it's almost a matroid. And it's in fact known, it's a delta-matroid. Okay, so what's a delta-matroid? Well, I've got my ground set E, and I've got my collection of subsets B. So you can think of these as playing the roles of bases of the matroids. In delta-matroid language, usually called feasible sets and denoted by F, but I'll just stick with B for this talk to keep life easy. So I've got my collection of subsets, and in a matroid, the bases satisfy an exchange axiom, and they do in a delta-matroid as well. They also satisfy an exchange axiom that's called a symmetric exchange axiom, which is just a version, a rephrasing, a particular rephrasing of the usual basis exchange axiom. So kind of all it's missing from the definition of a matroid is that in a matroid, all of the sets would be of the same size. All the sets in B would be of the same size. And we're just not requiring that for the delta-matroid. So you can think of a delta-matroid as just dropping what happens when you just drop the requirements that all of the bases have the same size in the matroid. Okay. So just 3 examples. So if this is E and B, this collection of sets B1, B2, and B3, these would all form examples of delta matrices. So a little bit of terminology. Okay, I've mentioned this before, that your delta matroid is precisely a matroid if everything in B has the same size. Okay. New bit of terminology, we say that a delta matroid is even if everything in the collection B has the same parity. So if every set is odd or every set is even. So this delta matroid would be even all of the sets are odd size. This would be even, so matroids are necessarily even. And this one would be an odd delta matroid because it's not even. So the other bit of terminology we need is the width. And what I'm going to do is I'm just going to look at all of the sets in my collection B, look for the biggest set and the smallest set, and take the difference of their sizes. So in this example, the width is going to be 3 minus 1, so the width is equal to 2. A matroid, so B, this is an example of a matroid. Everything of the same size, that's going to have a width 0. And the last one, what's the width? So we've got sets of size 2 and sets of size 1. So the width would be equal to 1. Okay. So what's going to, so we'll come back to these definitions. So these terms, so even if everything has the same parity, or everything in B has the same parity, and the width is just the difference between the biggest and smallest sets in B. Okay, so delta matroids, you could think of them as arising as what happens when you localize duality for matroids, but you can also do this for graphs as well. So remember, we're motivated by plane graphs. And I'm not going to tell you how to do this in this talk, but it can be done. So if I start off with some graphs, so I've got my little plane graph here, so a theta graph with a loop, I could form its full dual, so dualing all of the edges. But there's also a way, a nice construction to form a partial dual. So all I'm doing here is just taking some subset of edges. So in this example, I've taken the edges 1 and 2, so here and here, and I'm just dualing those edges, and I'm not dualing the other edges. And I get a new graph. It's a new graph in a surface, but the surface need no longer be the plane. So something has changed here, and it's taking you outside the world of plane graphs. Okay, so let's bring this back to the matroids. Well, what's happening? So let's think about cycle matroids. So I've got my graph, I'm a cycle matroid, I'm working in the language of bases. So my ground set is the edge set of the graph, and my bases come from the edge sets of the spanning trees. Okay, so here's my plane graph in yellow on this side, and here are the 3 spanning trees it has. So if I want to non-localize this, so how did we move from matroids to delta-matroids? Well, I formed partial duals. So I could just form the partial dual of this idea, and I could non-localize this definition, delocalize this definition. And under this, we've got, well, the trees under partial duality, they become what are known as quasi-trees. So what are these? Well, these are just subgraphs that have exactly one boundary component or one face. So what do? I have my graph in a surface, I take a neighborhood, so just cut it out and I see how many boundary components it has. And if you're careful, you could formulate this in terms of faces of the subgraph. It's a little bit awkward to formulate precisely. So what have I got? So under partial duality, my trees become quasi-trees. So I can just take this with cycle matroids, the definition of a cycle matroid. I've got my spanning trees, and I just replace these spanning trees, just delocalize, and I replace that with the spanning quasi-trees. And this, what I end up with, this pair is an example of a delta-matroid. Okay, and this delta-matroid is really playing the role of the cycle matroid in topological graph theory for non-plane graphs. Okay, so maybe just a couple of facts I want to mention, because we'll come back. Okay, so, well, if my graph is plane, all of the quasi-trees must be trees. That's the only way I can get one boundary component. So my delta-matroid is just a matroid and is identically the cycle matroid. Evenness in a delta-matroid, I can make use of Euler's formula and can show that corresponds to orientability. So my graph's orientable if and only if everything in B is odd or everything is even. They can all have different sizes, but they must have the same parity. And finally, this Euler genus, so remember this was twice the genus if you're an orientable surface, or the cross-cap number if you're in a non-orientable surface. And that's just the width of a delta-matroid. So that was the size of the biggest set in B, subtract the size of the smallest set in B. So what have we got when we've done this? So let's come back to the graph polynomials. And what did I do? So I went from plane graphs, I had the rank of a graph, and I got this topological version of the rank plus the Euler genus. Well, matroid the world, so I've got rank functions, and now down here I've got a way to get Euler genus. So I can go to my graphs definition, my graph polynomial. I had previously modified the rank function by adding this Euler genus. Well, I can just turn this into a matroid version and take the rank of the delta-matroid. Okay, so technically we need the matroid to take the rank, but if we take all of the smallest feasible sets, it's a fact that they form a matroid, and we just take the rank of that matroid. And for the Euler genus, I'm going to take the width, and this is my new parameter. I'm just going to call this sigma of D, just to give it some notation. And then I would take my ribbon graph polynomial, my 2-variable Ball-Bas-Riordan polynomial, or my top polynomial for embedded graphs, depending on what language you like, and just replace the G for graph for a D for delta-matroid, here and here, and I've got a new graph polynomial. And again, what have I got? I've got my beautiful duality formula. And again, that's without any restriction. Okay, so all delta-matroids. I can recover the graph result by taking this delta-matroid of the embedded graph. I could recover the plane graph result by just taking G to be a plane graph. I can, if my delta-matroid is a matroid, I get the matroid result. So what have we got sitting at the top here? Well, we've got delta-matroids sitting above all of this matroids, embedded graph, plane graph. Okay? So we started off, so let's think what we did. So we started off with this beautiful duality formula for plane graphs, this wonderful fundamental duality formula. And it was incomplete, so we just kind of followed it home to see where it would lead us. And what we do is we have to just understand it, we have to end up in this world of delta matrix. So we can take this philosophy and we can think about this. So we can think about this as just a general property for the Tutte polynomial. And for all of these wonderful results that hold for various restricted classes, so plane graphs and so on, we can start asking whether these are all delta-matroid results. And in many cases, they are, so particularly anything involving the medial graph, so evaluations involving medial graphs, very nicely in the world of delta-matroids. Most of the results that hold for plane graphs, I don't know yet. I don't know yet. Maybe. But there's something going on a bit, but something goes wrong. And there's something missing from this picture. In that there are results that that hold for the Tutte polynomial, and you lift them to the delta-matroid world, but they're still incomplete. So we've been following these results home, but we haven't quite found them. And I just want to take you through very quickly one of the examples of this. And this has to do with connectivity. And first of all, so earlier in the before times, I was in Prague earlier this year with Steve Noble and Andrew Goodall and Joel Monahan and Luis Vina. And so this is what the rest of the talk is all joint work with these guys. So the question is, well, let's look at connectivity and let's try and recognize it in this delta-matroid polynomial. So connectivity for delta-matroids, what do I do? Well, I just copy the matroid definition. So I can define a direct sum of a matroid. So I take the union of the two ground sets, and for my bases, I just take an element of B, each element of B, each element of B1, each element of B2, and just take the union of them to get my collection. So just the standard definition, you've seen this before. So what do I do for a delta-matroid definition of direct sum? Well, I just replace this M with a D, this M with a D, and these two M's with D's. Okay, so I'm just lifting the matroid definition. And then I say that my delta-matroid is connected if it's not a connect sum. Sorry, not a direct sum. So exactly how you would define this for a matroid. So for example, up here, if this is my E and B, this is not connected. Why is that? Well, I could take my two sets B, I could take 1 and 2, together with the empty set and the set 3, 4, and this guy is connected. I can't decompose this. So let's come back to the graph polynomials. So can you recognize connectivity and matroid connectivity or graph 2 connectivity with the Tutte polynomial? Yes, you can. So the Tutte polynomial, it's a 2-variable polynomial, integral coefficients of the variables x and y. So what I'm going to do is I'm just going to pluck off the coefficient of x and get a number out of it. And this is called the beta-invariant, and is denoted by beta of m, the matroid, and it was introduced by Craig. Here are some examples of beta-invariants. So the free cycle has 1, This graph here has 0, k forward up 2, the final plane has beta invariant 3. And a beautiful result of Crapo from 1967 showed that beta recognizes connectivity. So if you look at the beta invariant of a matroid, well, it's a fact that this is always non-negative. And if this is greater than 0, your matroids must be connected. So if it's 0, it's not connected. So where do you go with this? Well, follow the result. So if your coefficient of x of the top polynomial of a matroid determines connectivity, what can you say about the coefficient of x of this delta-matroid polynomial, this delta-matroid top polynomial? So I can go through this game. I can define a beta invariant by just plucking the coefficient of x. There's a little bit more going on here because unlike the matroid case, you can have the beta invariant is negative. So you have to watch for this. It's not the same object. But a lot of the results hold for the delta-matroid version. And in particular, this Crapo's result of Crapo, you can extend this to the delta-matroid setting. So as long as you've got your delta-matroid on 2 elements, and it's even, if the beta invariant is non-zero, your delta-matroid must be connected. So why is this? Let me give you a quick rundown. So in one direction, the easy direction, it follows because the graph polynomials are multiplicative under direct sum, and they have the constant term is 0 as long as you've got some edges. So what's that? And in the other direction, well, you're going to just use induction. So the top polynomial had a root deletion contraction relation. Well, so does this polynomial R for delta-matroids. It's more involved, but it's still a deletion contraction relation. And then you can make use of, to get hold of the connectivity, you make use of Boucher's chain theorem for delta-matroids from 2001, which tells you as long as you've got a connected even delta-matroids, then if you delete something and contract something, one of those resulting delta-matroids must be connected. And together with the deletion contraction allows you to reduce everything to the case of delta-matroids on 2 elements, which you can just check. Okay, so that's great, but something to notice here is that we're still getting this word even coming in. And in fact, well, more can be said about the beta invariant, more can be said about the beta invariant of delta-matroids as well. And jumping back to the matroid case, so one little fact is that as long as you've got 2 elements in your matroid, in the top polynomial, the coefficient of x is equal to the coefficient of y. So you could just read the beta invariant from y, if you liked. And this fact, what is it? It's just a linear relation among the coefficients of the top polynomial. So more generally, you could look at the t's, so coefficients of the top polynomial, and you could look for all linear relations, so alpha and gamma are just integers, say, and you can look for all of the identities that hold among the coefficients. And what you end up, so Brawlowski has done this, and you end up with a bunch of coefficient identities, which is every single relation between coefficients of this form. If you want to see them, the theorem looks like this. I don't think you want to stare at that too long just now, so let's just move on from that. Now, these are great things, the coefficient identities. They look quite technical, but they're really useful. And in particular, Marino, Demir, and Noy in 2001 got a wonderful result from these identities. That was the top polynomial is irreducible if and only if your matroid is connected. So that tells you that the only way you can factorize the top polynomial is the stupid one, is when m is the direct sum of something. And then the proof has key ingredients. So what have we got? So we've got the beta invariant results, because you need to know about the coefficients of low degree in the top polynomial, makes extensive use of Brolatsky's identities. There are some divisibility results in there, and they're also really, really smart people, so they use their brain there. But what have we got for the Delta-matroid polynomial? Well, we've got beta-invariant results. Not all of these Brolatsky identities hold, but a lot of them do, and you can make use of work of Gary Gordon from 2015, just to get a lot of the identities for free, in fact, using this rank function of the Delta-matroid. And again, in the Delta-matroid, you can start proving some divisibility results that you need. And, okay, well, I've got smart co-authors, but I'm not smart, but fortunately I can jump on the coattails of these smart folk. And by doing that, we can end up with a theorem that states that this Delta-matroid polynomial is irreducible if and only if G is connected, as long as you've got an even Delta-matroid. So again, what have we done? We've taken this result for the top polynomial and we've been tracking it home and it's taken to the world of Delta-matroids. Except there's a problem here in that, yeah, we haven't followed it all the way home. We've got this even condition here. So what have we done? Well, we've started off with just this nice plane graph results, and we've just chased everything backwards, and we've ended up through matroids, embedded graph Delta-matroids, and we've looked for that. And we've shown, but these results seem to be, so many of the results seem to be restricted to even Delta-matroids. So in fact, what we show is that the picture is incomplete. We haven't followed, our private detective hasn't followed these results all the way home. So there's something sitting above here. And the key thing seems to be, from what we've figured out so far, is that once you're dealing with odd Delta-matroids, you've got really three types of minors. You've got deletion contraction or twist contraction. And once you've got these three minors, that's really taking you from Delta-matroids into the world of multi-matroids. And I think I'm going to leave this for a story for another day, particularly because we don't quite know all of the answers yet. But it's quite stunning how you start off with this classic result just for plane graphs, and really to understanding it, you're really having to go up into the world of Delta-matroids for that. So I'll say thank you and stop there.
Thanks again for a very nice talk. Do we have any questions? Okay, I have a question which might be a bit pie in the sky. Is it possible to reconcile this with other generalizations of matroids? So I mean, polymatroids go in one direction and Delta-matroids and such go in others. Is there possibly some kind of common generalization of them? Could you go further?
Yeah, so kind of a lot of the story that, one of the things I'm interested in is chasing this result and finding out the right context. I'm obsessed with finding the right context for understanding a result. But with graph polynomials specifically, I'm one thing I like to understand, and it's a very vague statement, but it's understanding what results are results about the polynomial and what results are results about the object. So this is sort of, you're wanting some theory that allows you to say, okay, so you've got a top polynomial of this type of object, therefore all of these properties hold. And yeah, so Hopf algebras would be a concrete example of such a setting. And once you've got that, well, you're getting things like the duality formula, the convolution formula, and so on down to there. And maybe something that really seems tied to the graph world is things like orientations. I don't quite see many ways to look for orientations other than to find, well, I suppose they're matroids and signed matroids. So polymatroids and things like that, I don't know. And a lot of the difficulty becomes as a Hopf algebra, they're not connected in that you don't have a graded dimension of 1. So it looks like other things fit in these frameworks, but I'm not exactly sure what fits in, what doesn't.
I mean, even if it's a lot of work, would you be optimistic that such theories would exist?
I think there should be some general frameworks. The sort of challenge is not going too high level. So you want to have enough structure there so you can always say something.
Mm-hmm.
Yeah. So I think I'll avoid being tied down to an answer of that question.
Fair enough. Are there any other questions? Well, if not, let's thank Iain, and I will stop the recording.